Herbig-Haro objects are impressive jets emanating from stars in formation. The material in these jets propagates in opposite directions and along a straight line from the central star. The name Herbig-Haro or HH objects is given after the two astronomers George Herbig and Guillermo Haro, who first observed them in the Orion Nebula during the 1940s. But astronomers were not interested in these objects, but rather in the central star from which these originate. These protostars are called T-Tauri stars, which have a disk around them and is still gaining mass from the disk that they have around. In that stage, the light is not produced by the fusion of hydrogen in the core. What we see is actually the glow of the ionized material that the magnetic flux is channeling from the disk into the star's surface. The complex interaction between the magnetic field, the corona of the protostar, and the disk are likely responsible for the observed variability in these objects, for the production of the jets, and ultimately for the final mass that will have the resulting star. This complex interaction continues even after hydrogen is ignited in the center. At this point, it becomes a class 0 star, but is still considered a protostar because it is still gaining mass. Astronomers that study these objects agree that the presence of the magnetic fields is also responsible for the alignment of the jets and also for the periodic bursts of material. Some attribute this burst to a periodic pinching of the magnetic field lines due to the differential rotation of the star and the magnetic lines in the internal parts of the disk. Eventually, this produces what we call a plasmoid that propagates ballistically outward in these jets. The accelerated particles from the stellar wind and the magnetized jets hits the molecular and atomic material, making them observable in the visible, the infrared, and the radio light. Here, we look at two Herbig-Haro objects observed at the James Webb Space Telescope. Probably the most spectacular of this pair is the image of the Herbig-Haro 211, which shows amazing detail of the jets emanating from the central star. The central protostar is 3.5 times more luminous than the Sun, but very cold, just 33 Kelvin compared to the 5,500 Kelvin of the Sun, and is surrounded by a disk of dust and molecular gas that is almost one solar mass. With the James Webb Telescope, we see the structure produced by the molecules of hydrogen, the molecules of carbon monoxide and silicon monoxide, which are heated by the ejected material that is colliding with the ambient gas or slower moving gas there. The velocities of the innermost outflow structures is roughly 48 to 60 miles per second, while the outflow events producing the observed shocks happen after 425 and 295 years. Herbig-Haro 4647 is about 1,500 light years from us in the Vela constellation and is another of the objects that James Webb observed. As its name indicates, the jets are powered by two protostars shining bright in the center. Part of the light is buried deep in the disk of gas and dust, which provides more of the material that helps them to gain more mass. The disk is not visible, but its shadow can be seen in the two dark conical regions that are surrounding this bright central region. In this case, the Herbig-Haro objects is produced by two T-Tauri stars, making the pattern of the jets more complex. We have two strands in here. The right-hand side shows two bow shocks, one with a lot of material glowing behind the crest, while the other is just a faint ray nebulosity in the image. The jet at the left-hand side does not show bow shocks, probably because it's within the Bok globule, which in the image appears a very dim cloud like an elliptical structure. This globule is a cloud of dense dust and gas that is just a dark region when we see it in the visible light. But with James Webb, we can peer inside and see the structure of the jet with great detail. In this image, the most recent ejection appears in the right-hand side jet as a faint blue line parallel to the diffraction spike that James Webb produces. One of the oldest ejections is barely seen as a red bow shock at the top right corner of the image. As we can see, both of these objects are spectacularly full of details that help shed light on when and how the ejected material is produced and how these relate to star formation.